double strings 705 div2c. This is a question. Now this question can be solved via greedy approach, but I think that is cumbersome. So I've done a binary search based approach here, where so whenever we have whenever we have to check lexicographic ordering between strings, we generally an observation in these type of questions is that uh, a certain prefix of the string would be the same, and then uh, a character might differ. So if we want the string t to be lexicographically greater than equal to string s, then the string t will have I characters, the initial I characters, that is the prefix of length I, to be equal to the prefix of length I of string s, and then the I plus 1th character may be different in string t. By different I mean maybe greater than, or maybe greater than that ith character in string s, and the rest of the characters in t might be anything, the characters from I plus 2 index, because as it is from, since the I plus 1th character in string t is greater than the I plus 1th character in string s, we've established that t is lexicographically greater than string s. So let us say that let us define f of I as, can we get a beautiful string with indices 0 to I. uh, so what this statement means is that, can we get a beautiful string, can we make a beautiful string given that the initial given that the indices 0 to I are common in string s and the final string. um, yeah, this is f of I, and if we apply binary search, we'll get the maximum I for which this is possible. And if we are able to once calculate the maximum I for which this is possible, uh, we can then, for that particular I, we can generate a solution which gives us the lexicographically minimum string that is uh, beautiful, and for whom these characters, these indices are the same as these indices in string s. So, and the moving on to the time complexity would be order of log n times the time complexity of fi. Why it is log n is because of binary search, the complexity of binary search. Uh, yeah, and the time complexity of fi, as we'll see, is order of n. So the overall complexity is order of n log n. Uh, Now, okay, so let's think about f of I. How do we formulate this function f of I? Now, a very greedy approach which works in this case is that, uh, first first of all, copy all these indices to the string t. So by this I mean that, make t of 0 to I is equal to s of 0 to I. Assign this to this. Once this is done, for the I plus 1th character. So yeah, okay. So now maintain a map of 26 characters, storing what is the frequency of characters from in these indices. So once we have this, the minimum number of characters we require from indices I plus 1 onwards can be said that, for example, if we have MP of A is equal to 1 and K is equal to 3, from I plus 1 to from I plus 1 onwards, we'll need at least 2 A's, so that the total number of A's is a multiple of K. So in this way, we can store the minimum number of characters required uh, to make the string beautiful. If let's call that quantity nr. If nr plus the number of characters we already have, that is id plus 1. If nr plus id plus 1 this exceeds n, then uh, f of I would be 0 because we can't get a beautiful string. Else if nr plus else this is this condition. Else we have defined the nl as num left is equal to n minus nr plus id plus 1. Else after t0 to I add nl number of z's and then reverse sort the uh, map that we generated from t0 to I and put it here. In this case f of I would be 1. I'll show you in detail in code. So this is the code. It's a very comparatively lengthier code. So this is the okay. So the first and for all, if k does not divide n, we'll straight away get a -1. If it does, then this is the code for binary search. Funcmid is the function we are talking about. Yeah. So we've maintained a map. Um, this is handling uh, edge case when um, we have when we have already reached the end of the string. This is storing the number of nr that we just spoke about. This is the condition that we spoke about. This is exactly what I told you. Yeah, once this is done, we now after the binary search, we have to handle this case separately. And if so answer is basically the index, the last index for which t of I would be equal to s of I. Okay, if answer is equal to n minus 1, that means the string s itself is a beautiful string and report string s. Otherwise, the first answer indices would be the same for the answer for the final string. Then this this is a way to generate the final solution such that now we know that once we have answer, now we know that uh, with the first answer indices same in string s and t, we know for sure that we can generate a beautiful string. Now the only work left is to generate the lexicographically minimum uh, beautiful string. The algorithm for this is so once we have selected the first I answer indices, to select the next index, iterate over the 26 or whatever. If the answereth index was contained the character C, then iterate from characters D to Z. As soon as we encounter a character which is giving us the correct solution, we break and report the solution. So the way we check it is via this function, which is nothing but like we were doing here. Where is that? Yeah, for example, when we were checking for answer in the binary search, when we wrote the function f of I, we used to insert z's here. In the current function, the only change would be we would insert a's in between. Yeah, so everything is pretty similar here. The only difference is that yeah, this is the only difference. Yeah, this is the solution.